A piecewise function is a function that's defined by two or more equations over a specified domain. So what a piecewise function does is it maybe doesn't behave the same way all the time. If I just say f of x equals 2x minus 5, it's going to be 2x minus 5 no matter what. But what if I have a graph, whoops, I'm on a highlighter. What if I have a graph that maybe starts following one pattern, then stops and follows a different pattern, then maybe jumps up here and follows a different pattern? We can't use one rule to describe this function because it keeps changing its behavior. And so we use what is called a piecewise function. What that means is we're going to define it in pieces. This function would have 1, 2, 3 pieces that we would need to define separately. In real life, functions are often going to be needing piecewise functions, okay? Here's an example of a situation that would require a piecewise function. So it says, a cell phone company offers the following plan. $20 per month buys 60 minutes of talking time. Additional time costs 40 cents per minute. This is how it costs to get a cell phone when cell phones first started coming out. Now everything's unlimited, but we don't have to see it a lot like this anymore. I know this says on the next page, but it's not the next page now. So here's the idea. No matter what, we pay $20 for the first 60 minutes. So the first piece is a constant value of $20 as long as I talk somewhere between 0 and 60 minutes. The second piece of the function pays for the $20 that I paid for my first 60 minutes, and then 40 cents per minute times the number of minutes after that first 60 that I've already paid for. So this is exactly the point of where we have to use one function to describe the first 60 minutes and then another function to describe the next 60 minutes. So the most important part of a piecewise function is the domain for each piece. So that's how we decide when to use which rule. The first rule, C of t equals 20, applies for t values that are equal to 0, greater than 0, but less than 60 or equal to 60. The second function, C of t equals 20 plus 0.4 times t minus 60, that piece only applies for t values that are greater than 60. The graph of this would look something like this, where we would go from 0 to 60 at $20, and it would stay $20 the whole way. Then after that, the price starts increasing because it changes after those first 60 minutes, okay? Now, the way that we read a piecewise function is to choose the rule based on where the value fits. So if I want to evaluate different values for C of t, like for example on number 4, C of 30, I need to decide into which of these intervals does 30 fit. And 30 would fit in the first interval between 0 and 60. So that means we use the first rule, which is just 20. If I want C of 100, 100 is a number that is greater than 60, so I would need to plug this into the bottom rule. 20 plus 0.40 times 100 minus 60. So that is 20 plus 0.4 times 40. And that comes out to $36. So if you speak for 100 minutes on the phone, your total bill is going to be $36. Let's pause the video real quickly to do a little mental check yourself. Try number 6 and 7 and see if you can determine those values reading correctly off of the function. Answers coming in 3 seconds. So in a similar way, you should get 20 because 40 falls into the first rule, and you should get 28 because 80 falls into the second rule, okay? So that's the first trick, is kind of how do we read them. The tricky part now is how do we graph them? And then we always want to determine the domain and range. So I'm going to do a couple of these. I'll leave the rest for you to look up in the PDF of the notes and try on your own. So for number 8, we have 2 pieces. We have x plus 2 if x is less than or equal to 1, and 4 if x is greater than 1. So the way that I always set this up is I always make tables. You may come up with a faster way to do this, especially if you notice that it's linear or quadratic or however you want. But this way is always going to work, and I think this organizational strategy will help you out with this a lot. So I have 2 pieces, which means I'm going to need 2 tables. I'm going to have x, and I'm going to have x plus 2. That's the first piece of this piecewise function. And then I have x, and I have 4, which is the second piece of this piecewise function. Now, no matter whether it's equal to or not, 1 is the starting point for each of these functions. You may have an open circle because you don't ever get to 1, but it is still the boundary point. So I'm going to start each of these tables at 1, and before I go any further, I'm going to decide if it needs an open circle or a closed circle. So for x plus 2, that's when x is less than or equal to 1. Equal to means I want a solid dot at that starting point there. But for 4, it's only greater than 1, not equal to, so I need an open circle when I draw my first dot for that one. I always set it up like this. I always decide open or closed at this point right off the bat. It'll save you in the end, I promise. So now for the first one, again, the rules are x's that are less than or equal to 1. So when I pick table values, I need to pick x's that are going down from 1. So I might look at 0 and -1. On the other side, I need x's that are greater than 1. So I might look at, say, 2 and 3. I may not need that many points, but I'm going to start with that and go from there. So now let's plug those numbers in. So 1 plus 2 is 3, 0 plus 2 is 2, -1 plus 2 is 1. So let's graph that section. We start at the dot and we go towards the arrow. So 1, 3 is going to be our first dot, 0, 2 is our next, and -1, 1 is our next. Notice, again, this is just my own personal strategy. You can do whatever you want. Notice how I made the starting point a little bit bigger than all the others. That helps me remember that I start there and draw my line through the rest, rather than drawing maybe this way and getting confused, which is something that happens when you're drawing these. So that's our first piece. Now the other piece is going to be a constant function. So no matter what I plug in for x, it's going to be 4 for the y no matter what, because it's always equal to 4. So at the point 1, 4, I draw an open circle. And then I have 2, 4, and 3, 4. And so we'll connect it like this, and then it goes on forever. So that is the graph of our piecewise function. Now the domain, the only real point that's in question, I start at an arrow, I end at an arrow, but the question is this section right here. And since there is a solid dot at 1 on one of the pieces, that means we're going to include it. So the domain for this graph is going to be -infinity to +infinity. The range, we've seen ones like this, is a little bit trickier. It starts, if I read the graph bottom to top, the first place I start at is an arrow at the bottom, so that's -infinity. But then I go up to 3, and I'm equal to 3, but that's where the graph stops. And then the only other y value that ever gets after that is 4. So we would say union 4. That is how we would write the range. That's something that we practiced in Unit 1. So that's how I like to approach these. Let's look at another one. Let's see what I've got here. Okay, let's do number 10. Number 9 is very similar to that one, but let's look at 10 because this one has some interesting pieces. Okay, so in a similar fashion, I want to graph each of these pieces. So I'm going to set up my table. I have x and I have 1/2 x squared. and I have x, and I have 2x minus 1. For the first one, it's when x is less than 1, not equal to, so this one is an open circle. Both of these are going to start at 1 because that's our boundary point. And this side is the one that is equal to 1, so we want to include it. So I want less than 1 on this side, so I'm going to go 0, negative 1, and because this is a quadratic, I'm going to want a few more points to make sure I'm getting the right shape of my graph. And then for x, or for the next table, 2x minus 1, I want to go greater than 1, so let's say 2 and 3. All right, so let's plug them in. 1/2 times 1 squared is 1/2. 1/2 times 0 squared is 0. 1/2 times negative 1 squared is 1/2. And 1/2 times negative 2 squared is going to be half of 4, which is positive 2. On the next one, if I plug in 1, I get 2 times 1 minus 1, so that's 1. 2 times 2 minus 1, that's going to be 3. 3 times 2 minus 1 is going to be 5. So there are our tables. Now let's go to our graph and see what it looks like. So at the point 1, 1/2, I need to have an open circle. Then it goes to 0, 0. Then it goes to negative 1, 1/2. And then it goes to negative 2, 2. And so it's doing kind of what we expect a parabola to do. We're going down towards the vertex and then back up. So this piece looks like a piece of a parabola. And then on the other side, we have the point 1, 1. So make sure that doesn't bleed into your dot because it's not connected right there. Then we have 2, 3, and 3, 5. And so we connect this way. Now the domain and range for this one is a little bit more interesting. The domain is just like the other one. We've covered everything to the left of 1, everything to the right of 1, and 1 was included in one of the pieces. So the domain is negative infinity to positive infinity. It doesn't have to be that, just in general terms, but a lot of times it's going to be. Now the range, if I look right here, I have to make a little jump over here, but that jump is covered by this section of the graph. So it looks like the lowest y value is 0, and then some part of the graph covers everything moving up for the rest of the way, and so the range will go up to infinity. And so your practice right now is to practice with reading and interpreting piecewise functions and graphing piecewise functions. That's your focus for today, and I will see you later.